Thank you. Thanks, Ali, for inviting me. So my name is Nicholas Tripcevich, or Nico Tripcevich, from the Archaeological Research Facility. I'm the laboratory manager and a research associate over there. The Archaeological Research Facility, or ARF, has been around for almost 60 years now. And it was formed by, it was primarily anthropologists early on, and then they reached out and involved faculty from other departments like classics, and it also includes faculty that contribute to archaeological knowledge without necessarily practicing archaeology themselves, such as geochronologists, paleontologists work in our lab sometimes, and earth and planetary science faculty, palynologists, and others. So there's 38 affiliated faculty and their graduate students and associated researchers. So when there's archaeologists on campus and other departments that are looking for affiliation in connection to other archaeologists and perhaps access to lab space and instruments, we can provide that in many cases. We have lab facilities in our building that are used for things like bringing in soils from foreign countries where the U.S. Department of Agriculture is very concerned about contamination from foreign pests, and so we can quarantine them in our labs. We have equipment for things like phytolith extraction, which is ancient silica bodies. I'm going to talk about those a little bit more later. And we have microscopes and a small GIS lab with a plotter and things like that. We also have quite a few field instruments, and these are really important for archaeologists because it's a intense time when we go out into the field and we try to get a lot of information quickly and efficiently and bring it back without losing any information. So reliable equipment is a big part of the ARF, and we have mapping instruments. We have ground-penetrating radar and other types of remote sensing instruments for near remote sensing. And then we have GPS, a whole suite of GPS units that we lend out to archaeologists. So archaeology is generally broken up into 3 stages, and so I'm just going to outline these and present them in my talk in terms of those 3 stages. So one of the first things archaeologists wonder about is where are the sites, and is something an archaeological site? So that would be stage 1, is looking for sites, identifying them, and then keeping an eye on them perhaps in the future. So one of the important things we do is survey, prospection, and monitoring. You've maybe heard about there's been a lot of press about Sarah Parsec and her satellite-based archaeology and monitoring site looting and also discovering new sites, maybe a new Viking site in Newfoundland. So there's quite a bit of work going on with satellite imagery in archaeology these days. New satellite platforms like Worldview 3 are providing down to 1-foot resolution data. So you can really keep an eye on places like the looting pits in Egypt. Professor Carol Redmount's work has been basically halted by the events in Egypt lately. And so you can see these pits going in remotely sent satellite imagery data. It's also used to identify sites, as I mentioned, like that Newfoundland site. So changes sometimes in vegetation can be perceived from satellite imagery that reveal sites hidden in the ground underneath because there's like different soil or walls underground that are changing the way the plants grow. There's also been a lot of press about LIDAR, light imaging detection and ranging, which is a method of sensing topography, and also it can, using different wavelengths, can map surfaces under the tree canopy from aerial LIDAR platforms. And so that's been used quite a bit in the dense forests of Central America and other places for detecting archaeological features. We also have we recently acquired a Phantom 2 UAV, and we had a talk from 3D Robotics, so we're definitely paying attention to the developments in drone technologies. These are really good for mapping archaeological sites while you're working there. Sometimes archaeologists can afford to hire a plane to fly over, but usually it's not right when you need it, like after you've finished excavating and revealing something interesting. So with the drone, you don't need to schedule anything. You can just send it up and take images of features from above. And then finally, in terms of remote sensing, this is very near surface remote sensing, right? Dragging over the surface is how we use geophysical instruments to detect features underground. This is an important development in archaeology, partially because excavating and exposing ancient deposits is sometimes controversial or not desired. And so we can often detect and map things without actually digging them up, and maybe avoiding things that we would rather not dig into by using these different types of instruments. These basically complement one another. One of them, the magnetometer, is essentially a very sensitive magnetic detector or metal detector. It's so sensitive it can pick up iron particles and changes in iron, the magnetic alignment of iron in rocks that have been heated very heavily in, say, an ancient forge or things like that. We have a ground-penetrating radar, which sends radar signals into the ground, and we have a resistivity meter. And there's several designs of resistivity meter, but the one we have, you put in a whole array of probes, and it iterates between them and detects. The further apart they are, the deeper it goes, and it moves through, and it maps out the resistance in the soil. So I was going to show you a few examples of how we look at these data, because this is one of our data science-rich applications in archaeology. So here's an example of both magnetometer and radar in use. One of the reasons we work at the same time like this is because setting up the grid is a big part of the work. So we lay out grids, sometimes using a total station to map it in, and often just laying out tape. We'll use non-metal tapes because the magnetometer will otherwise pick up the metal. And we'll map out a site like this. In this case, we're at Fort Ross in Sonoma County, California, which is a beautiful Russian early 19th century site. And there's the stockade, if any of you have ever visited Fort Ross. That's a very well-defined wall and orientation of the stockade. And the village adjacent was at a different alignment. And we think we can detect an old road and some old house foundations by mapping this unmodified area adjacent to the site. So that was us at work at one place. This is another historical site here in Northern California, Carrillo Adobe in Santa Rosa, California. And here's an example of what the data looks like. So you can see that in the magnetometer, we have, this is the Adobe, this is the present, oh, do I have a pointer? Yeah. This is the present structure, and that's why there's a white spot here, because there's a building there. But they did magnetometer, and they detected certain things. This may have been a underground pipe, so you can pick up the metal things really well, whether you like it or not. And then you can see this right angle. And in the radar, they also picked up a right angle. And this white line is showing where a profile, in my next slide, I'm going to show you a profile taken here. And then finally, in the resistivity, there's also a right angle in the middle, south of this building. So this method is it's called a passive method, because it's just picking up the ambient magnetism. And there's not as much you can do with these data. You can sort of change the color spectra, but it picks up a lot of ambient magnetism, so it's getting a lot of noise from overhead power lines and things like that. So it has some limitations. Each one of these has pros and cons, basically. The radar, you need good contact with the soil, but it's pretty resistant to modern magnetic interference. So, and the other good thing about radar is that it's active, so you get more data about the size and shape and depth of the features underground. And finally, resistivity is relatively slow, but it's also an active method because you're sending the energy into the ground. Okay, so here's the cross-section of this profile. Can anybody see the wall feature that the analyst picked up in this image? That's what they saw. It was basically these peaks were kind of erratic, and then right here there's a pretty constant level, and then it drops off again. And he did these profiles all the way down this image. He could look at this section and this section and this section, and all of a sudden this wall appears. And based on the size down here in meters, you can evaluate it and connect it to maybe what you see on the surface. So this really guides us in our excavation plans and our site protection plans. And there's a lot of potential for visualizing things like this. This is very rich data, and we're just scratching the surface. So part of my pitch here today is to invite data scientists to do more with these data with us, because we are gathering more and more rich data like this at our sites, and can't really keep up with all the developments. Another big part of this is aligning historical data. So this is kind of a neat project that I'm involved in as a GIS user. We get these beautiful 1 to 5,000 scale maps from the Coast Survey in the 19th century. This is a 1863 map showing these structures that were abandoned by the Russians when they left. And back in 1892, these buildings were still there. 1862, I can barely read that. 1862, these were still there. This is Bodega Head in Sonoma County. Perhaps some of you know what happened there later in the 1960s. PG&E decided it was a great place to put a nuclear power plant, and they scooped this whole thing out, and they call it hole in the head. So they just completely scooped out the archaeological site, and it's probably somewhere over here now, but we think one building remains. So they didn't put the nuclear energy site there, luckily, because it's on a fault line. But anyway, they got rid of 2 of these 3 sites, and we're looking for this building now. So step 2 is testing and excavation. And one thing I'm just going to mention briefly about this is there's a lot of possibilities with enhanced fieldwork for surveying and for excavating. That is, for walking over the ground looking for sites, and also for excavating and documenting the sites. I've done quite a bit of work in ArcPad before there was nicer mobile systems like iOS and Android to work on. And so this is the kind of thing we can develop using customized mobile interfaces. So here we have a drop-down menus that are customized to our site our research questions. We can do things like sampling grids, guided sampling grids. We can work on predictive models. You can reference existing layers and go and look for things like soil maps and things that other specialists have found. It's like bringing a geologist with you into the field to have a good geological map. So land management layers and other things. You could have an alarm that goes off that says, hey, this is a high probability location for an archaeological site. Keep your eyes open. That kind of thing can be built in a mobile interface. Field correction, finally, is an important part of field work and ground truthing. And then finally, there's a major task for archaeologists is reporting on our findings. And there's been a lot of developments in how we document archaeological materials and report them. So one of the big improvements lately is how photogrammetry and laser scanning have really advanced. And photogrammetry has gotten to the point where you can just take 4 photos like this. These are the position of the shutter of a digital camera, and software like AGI Soft Photo Scan can stitch these together and produce a 3D model when there's a sufficient overlap between them. It reconstructs where the camera lens was located. It doesn't need to know ahead of time, which is how classic photogrammetry functioned. So we use it for artifacts like this. Oh, okay, that slide was out of order. And we also use it for site documentation. So this is an example of using PhotoScan Pro with overflight drone imagery. So again, you can take just multiple photos, and this software can stitch it together and create a 3D model that you can take measurements on. So this is a big improvement over traditional site mapping for archaeologists. And then another example of artifact reporting and repository in archaeological information repositories is, here's an example with obsidian geochemistry. We have a number of methods for analyzing artifacts and learning about maybe where they came from or how they relate to other artifacts in our collections. And with obsidian, because it's a volcanic material, the chemistry, the trace element chemistry is unique for each volcanic eruption. So you can analyze an obsidian artifact like this projectile point with an instrument like this portable Bruker. It's about the size of a hairdryer. and get trace element information on these elements like strontium and rubidium. And a big part of the challenge then is to connect the chemistry with existing databases of different obsidian sources that tell us about the geological source of that rock. So it's sort of a burdensome task is to look back through all the different recorded chemistry and compare each artifact with that. So I'm currently working on a project to develop a web visualization interface to compare artifact geochemistry with existing collections of already analyzed artifacts and source materials. Finally, another example of repository and artifact analysis is collections of microscopy images like this. Phytoliths, these silica bodies I mentioned earlier, they can last up to 300 million years. I was amazed to learn from a paleontologist. So you can learn about what dinosaurs were eating 300 million years ago. But they're also very informative in the recent times. For example, in the Holocene, people are learning about maize domestication and their wild ancestor Teosinte. And you can see the change in the silica bodies that are these resilient little silica bodies between wild and domesticated maize. So when people are excavating sites, say 5,000 years old in central Mexico, they can determine if it's wild or domesticated. One project people would be interested in developing is a library of images like this, and maybe automated routines for comparing these phytolith slides one to another in order to streamline the process of linking these and creating a database. So in sum, these are some of the methods that I talked about. So we have geophysical approaches. These are rich geophysical data sets, 3D models of artifacts that, there's all these immersive experiences in 3D now. Like I hear Davis has one of those caves where you can, virtual reality cave. So I don't believe there's one at Berkeley, but that's the kind of thing that we could really explore with some of these data sets we're gathering. Artifact geochemistry libraries and image classification algorithms, whether it's from satellite image classification down to microscopy image classification. So we're on campus. We're over by the Bolt School of Law, Berkeley Law Building, just this side of it. If you're interested in knowing more about this, we basically have great content. We need some help analyzing all the data we're collecting. So if you guys have data analysis skills, we'd love to work with you. If you want to receive our weekly emails, you can subscribe on our website here. And it's just like a condensed list of all the archaeology events on campus. So join us. Thanks.